Open a random GitHub repository and look at its commit history. You will see names, timestamps, profile pictures, and messages that make the project look completely human. But some of that code may have been planned, written, tested, and committed by an AI coding agent. And unless the developer or the tool leaves a very specific clue, you may never know. A recent study tried to measure this invisible workforce by scanning more than 180 million Git repositories across GitHub, GitLab, Bitbucket, and other public platforms. The researchers were not simply asking whether developers use AI autocomplete. That would be almost impossible to detect from public Git history. They were looking for stronger traces left by coding agents that can inspect repositories, modify multiple files, run terminal commands, fix tests, and sometimes create commits or pull requests with very little human involvement. And the first thing they discovered is that there is no single reliable way to find them. Some agents use a dedicated bot account. That is the obvious case. The author field might contain OpenHands, CodeRabbit, or another recognizable automated identity. Search for that account, count its commits, and measuring AI activity appears relatively easy. But many coding agents do not work like that. Some reveal themselves through commit messages. A commit might contain standardized text such as generated by Replete, generated with Claude Code, or a co-author line identifying an AI tool. These clues are not necessarily visible in the normal author field. You have to search inside millions of commit messages to find them. A third category hides inside human attribution. Some tools allow the developer to add the agent's name to their Git author information. The commits may still appear under hundreds or thousands of different human-controlled accounts, so searching for one central bot identity finds almost nothing. And then there are silent agents. Their strongest trace might not be a commit at all. It might be a configuration file such as claude.md, agentsa.md, gemini.md, copilotinstructions.md, or .cursor rules. These files give an AI agent instructions about the project. They can explain the architecture, coding standards, testing commands, preferred libraries, naming conventions, or files the agent should avoid changing. In other words, they function almost like onboarding documents written specifically for machines. But finding one of these files does not prove that every later commit was written by AI. It only proves that the repository was prepared for an AI coding workflow. This is why the headline numbers are so easy to underestimate. In one snapshot covering the major 2025 adoption wave, searching only for Claude's official bot identity found 28,154 commits. But when the researchers combined the bot identity with commit message signatures and other attribution methods, they found 850,157 distinct Claude Code commits. The simple bot account method recovered only around 3.3% of the combined result. That is roughly a 30 times difference depending entirely on how you search. And even the larger number is not the true total. It is only the activity that left one of the signatures the researchers already knew how to detect. Imagine that a developer opens Claude Code inside a local repository. The agent reads the codebase, edits 5 files, adds tests, runs the test suite, and fixes an error. The developer then reviews the changes and creates a normal commit under their own name with a message like fix authentication issue. From the outside, that looks like a completely human commit. There may be no bot identity, no AI-generated message, and no co-author trailer. The repository history tells you what changed, but not how the change was produced. By the April 2026 snapshot, Claude Code was linked to more than 886,000 commits during a 5-month window. Across the commit-attributed agents measured in that period, the study counted more than 1.7 million commits. Monthly detected activity peaked above 320,000 commits, with Claude alone representing around half of the total. But once again, these numbers should be treated as a detectable lower bound, not as a complete census of AI-written code. Configuration files reveal a different layer of adoption. Claude-related configuration appeared in more than 21,000 distinct projects. Around 66% of those projects also contained a Claude-attributed commit during the same snapshot. That supports the idea that many configuration files represent real, active usage, but the remaining projects cannot automatically be labeled inactive. The agent may have been used without leaving a recognizable commit signature. The configuration may also have been added for future use, copied from a template, or included by a framework. The disconnect becomes even clearer when we compare commits with pull requests. Another dataset called ADEV cataloged more than 932,000 agent-authored pull requests across approximately 116,000 GitHub repositories. In that dataset, OpenAI Codex dominated with more than 814,000 pull requests, yet the commit-based census found only a tiny number of comparable Codex traces. Claude Code showed almost the opposite pattern. The commit-based study detected hundreds of thousands of Claude-related commits, while the pull request dataset contained only a few thousand Claude pull requests. A pull request-only census missed a large majority of the Claude Code repositories discovered through commit history. This does not necessarily mean that one study is right and the other is wrong. It means different agents enter a repository through different doors. A cloud-based agent may receive a task, create its own branch, and open a pull request. An editor-based or terminal-based agent may work directly inside the developer's local environment. Its changes may be committed by the human developer without ever creating an agent-labeled pull request. The merge strategy can erase evidence as well. A pull request might originally contain 10 clearly attributed agent commits, but if the maintainer uses squash merging, those commits can become one clean final commit written under a human account. The code remains. The original attribution disappears. GitHub supports co-author trailers, but those trailers only help when the agent adds them and the developer's workflow preserves them. This has an important consequence. The detection method does not just change the number of agents we find. It can change what we believe those agents are doing. In the study, pull request agents appeared more focused on creating new features. Direct commit agents appeared more focused on maintenance, bug fixes, and smaller changes inside existing systems. Devin provided one of the clearest comparisons because it appeared in both channels. In pull requests, feature development represented around 45% of its classified tasks, while fixes represented approximately 27%. In direct commits, feature work fell to around 21%, while fixes increased to roughly 46%. So asking, what kind of work do AI agents perform, may not have one universal answer. The answer depends on the tool, how it is deployed, who is using it, and which trail researchers choose to measure. A cloud agent receiving clearly defined tickets may naturally produce larger feature-oriented pull requests. A local coding assistant working alongside a developer may spend more time fixing tests, updating dependencies, refactoring functions, or making small maintenance changes. The measurement system can shape the story we tell about AI development. All of this creates an open source transparency problem. But not because every invisible AI commit is automatically dangerous. The study did not prove that AI-written software is universally less secure or lower quality. Some agents produce larger changes than human contributors in the same projects. Other agents were used heavily for bug fixes and maintenance. A large commit can create more review pressure, but commit size alone does not prove that the code is incorrect. The more important issue is provenance. When a contribution enters an open source project, maintainers need to know where it came from, what tools produced it, what testing was performed, and who reviewed it. A human contributor might understand every line they submit, or they might have asked an agent to make the entire change, glance at the diff, and clicked merge. Those two commits can look identical in Git history. This matters because coding agents do not just generate isolated snippets anymore. They can read instructions, explore a codebase, choose files to modify, install packages, execute commands, and react to test failures. That makes them far more useful than autocomplete. It also gives them more opportunities to make confident but incorrect decisions across multiple parts of a system. There is also a software supply chain problem. A small AI-generated change inside an obscure open-source library may later be downloaded by thousands of applications. If the change introduces a subtle security flaw, the impact may spread far beyond the original repository. And if the commit contains no reliable AI attribution, future maintainers may not even know that the change was produced through an automated workflow. Reproducibility becomes harder as well. A developer can usually explain why they wrote a particular implementation, but an agent's output may depend on its model version, system prompt, tool permissions, repository context, and the exact files it was allowed to read. The same prompt given to a newer model a month later might produce completely different code. A commit preserves the final output, but not the process that created it. Licensing creates another difficult question. Open source projects often require contributors to certify that they have the right to submit their work under the project's license. An AI agent cannot personally make that certification. A human still has to accept responsibility for the contribution. But what happens when that human did not write most of the code and cannot fully explain where every part came from? Copyright adds another unresolved layer. In the United States, AI assisted work can still receive copyright protection when humans contribute sufficient creative authorship. But prompts alone may not be enough. A modern repository may contain human written code, AI completed functions, agent generated tests, machine written documentation, and entire features created through autonomous workflows. The legal result may depend on the exact process and the jurisdiction. And today, Git history rarely captures that process. The study itself also requires caution. It is an RXIV preprint, not a final universal census. Its detection techniques achieved high but imperfect accuracy. Configuration files measure preparation or adoption, not guaranteed usage. Known signatures can change as tools update their behavior. Developers can remove attribution text. Silent autocomplete is mostly invisible. Private repositories are outside the public dataset. And an AI agent can imitate a normal human workflow so closely that no public trace remains. So the safest conclusion is not that AI has already written a specific percentage of GitHub. We simply do not have enough information to make that claim. The stronger conclusion is that our software history is losing the ability to answer one of its most basic questions. Who or what made this change? Git was designed to track authors. It was not designed to track collaborations between humans, autocomplete systems, terminal agents, cloud workers, and autonomous coding tools. The author field tells us who submitted the comment. It does not necessarily tell us who produced the implementation. In the future, repositories may need standardized AI attribution, model information, agent configuration records, review metadata, and clearer declarations of human responsibility. Not because AI-generated code should automatically be rejected, but because maintainers cannot evaluate risks they cannot see. AI is not quietly replacing every open source developer, but it is quietly becoming one of open source's largest contributors. And right now, millions of machine-assisted changes can pass through our software ecosystem while looking completely human. The code has an author name, but that does not mean we know who wrote it.